Hello, I'm back again to one of my new videos about making my own AI chip. Last time we got to know a little bit about System Verilog, which is the programming language to program the hardware circuits for the chip itself. We got to know the basics about that. And now we will be getting to know more about the platform where we will be writing the programming language in it. So we more specifically, we're gonna be learning about the Quartus Prime from the company Artera that belongs to Intel, the big giant semiconductor manufacturer. And um, we got first to again know about the some tutorials in order to get to know more about the tools, where to write, how to run the code, how to execute it, how to follow up the errors, and also um, like how what is the best way to simulate the tool. First things first, let me share my screen in order to see what I have here. So I found this is here after a search. I find like this tutorial is interesting. Well, basically this is the tool I'm talking about. So I installed it, and installing it should be straightforward from the website on the Windows, and then starting a new project, then it should look something like that. But I wanted to show something else. All right, here we go. I wanted first to check that the audio is okay. All right, audio is okay. Then we go straight forward for oh man, for starting our tutorials. Okay, so the first tutorial he just talked about the platform itself, and now we're gonna dive more into um, yeah, into how to write code.
You can click New in the File tab, or you can press Ctrl-N on Windows. A window will appear with a number of different file options. You want to select Verilog HDL as your file type. Now you can start writing the module. You want to start by writing the keyword module, followed by the module's name. Next are the module's ports. They go in parentheses after the module name. Input ports are similar to arguments in a C function. They supply information that influences the module's calculations. Output ports are like the return values of a C function, but there's no limit to the number of output ports you can have in a Verilog module. Unlike functions in a language like C, Verilog modules are intended to represent physical circuits, where components are connected by wires. Often a module will need
All right. So yeah, so this is where to write. And again, I have to remember you that he is programming here in Verilog, even though it is more like first like more modern to use system Verilog, which looks a little bit different, but at the end it's the same. Only the syntax differs a little bit. But here is the input. He defined the input after the word module.
More than just one wire to send all the relevant information to another module in a timely manner. So limiting modules to just one output port wouldn't really make sense. The order the ports are written in doesn't matter, but you do need to put a comma after each port declaration with the exception of the last one. Do not put a comma after the last port as it will not compile. You'll need a semicolon after the closing parenthesis too. Also, by default, ports are only 1 bit. You will eventually learn how to make ports with multiple bits. After the ports comes the body of the module, where the logic happens. The simplest module simply combines the inputs in a Boolean algebra equation and returns the value as an output. This can be done with an assign statement, like so. The assign keyword is required, as the output is not a variable like in C. The assignment permanently wires the output to produce the value. For this reason, an output port can only be assigned once. Later in the course, we will learn how to produce outputs that can have variable logic. Lastly, you need the end module keyword at the bottom. To save your module, just press Ctrl S, or click Save As in the File tab. You'll want to give this file the same name as the module itself. So to recap, in this module I've taken the inputs A and B, which are both 1 bit, and performed a Boolean multiply, otherwise known as an AND operation, on them. Using an assign statement, I've wired the result to the output port called out, which is also 1 bit.
And here I wanted to emphasize that the guy has used same like the name of the file is the same as the name of the input itself, which is pretty cool. So here, after he write this first modules, so it looks like he's gonna be writing more than one module, and then he will be connecting them together.
Allow you to create a reusable circuit that can interface with other components of your design. Often, a module performs logic that is useful to another module, so the modules need to communicate. There are a couple ways to connect modules. The first way is by instantiating a module within another module. For example, every Quartus project has a top-level module that contains instances of all the modules used in the design. In Lab 2, you will have named your top-level module System. Let's instantiate a module in System. The instantiation syntax is similar to the syntax used when declaring a module in a module file. You first want to type the name of the module being instantiated. And after that, you type the name of this particular instance. We'll just call this AND1, but you can name it whatever you want. Next, you have to wire the ports. There are 2 ways to do this. You can simply list the port connections in the order that they are declared in the module file, but this isn't usually recommended because it requires you to keep track of the order, and modules can have a large number of ports. The more standard method is to specify each port and its connection individually. For the myAnd module, the ports are A, B, and out. So to connect port A, I'm going to type .A, and then a space, and then the port connection goes in parentheses after the space. In this case, I want to use the system port A as the input, so I put A in the parentheses. Notice how both A's refer to different things. The first A after the dot is the port of the myAnd module. The second A is the port to the system module. It just so happens to have the same name. If I change the system port name to Flying Fish, then I would have to change the connection to reflect that, but the myAnd port would stay as A. There are more ports to connect, so I have to place a comma after this port connection. I'm going to do the same thing with port B. And then for port out, I don't have anything to connect yet, so I'll leave the parentheses blank for now. Don't put a comma after the last port. It will compile in Quartus, but it won't compile in ModelSim, which we'll be using a lot of later in the course. Now I'll instantiate the ports for the myInverter module. The ports are A and out. I won't connect A yet, but out should be connected to the system out port. This brings us to the second way to connect modules. Within a higher level module, you can connect an output port of one module to the input port of another module. Physically, you would do this using a wire, so the keyword for the connector is also wire. Simply type the wire keyword and the name of the wire, and you can use it to connect two modules. You can connect the wire to as many input ports as you like, but it can only connect to one output port. Otherwise, it would receive conflicting signals. Now I'll connect my AND and my inverter using the wire. And now the system module is finished. By connecting multiple smaller modules, I've created a larger module that acts as an AND gate.
I've been thinking a lot about space lately, specifically this space out back, and how I can turn.
Even if a project compiles successfully, there can still be errors that cause the design to malfunction. Oftentimes those errors are caused by wiring the wrong modules together, or forgetting to connect one of the ports in a module. Quartus provides a helpful tool called the RTL Netlist Viewer that helps identify these errors. When the project compiles, Quartus generates a block schematic of your project, complete with modules, gates, and wirings. Let's take a look at the RTL for this project. First, compile the project. Then go to the Tools tab and select Netlist Viewers, and then RTL Viewer. The default view is from the perspective of the top-level module, in this case, System. We can see the instances of my AND and my inverter contained in System, as well as the wiring between those modules and the ports of System. You can click the plus on a module to expand the view of that module. For AND1, we can see the assign statement represented as an AND gate in the schematic. If we want to go back and look at System, we can double-click the module and the navigator on the left. If you have a mouse, you can hold Control and use the mouse wheel to zoom in and out. Otherwise, you can use the options in the View tab. Looking at Inverter 1, we see the assign statement as a NOT gate, as we'd expect. Now let's see what happens if we introduce a faulty connection into the design. I'll go ahead and remove the connection between Inverter 1 and System. It will compile, but when we go to the RTL viewer, the mistake is clear. Compare this to the correct schematic. Sometimes it can be hard to spot a misconnection if you're working with a very large project. If you suspect you might have miswired something but can't find it in the RTL, you can check the Warnings tab. Right here it says, Output port system out and system has no driver. So you see that even when it compiles, Quartus does notice the misconnections. Now I'll go over the process of adapting your design to an Altera FPGA board.
So basically, I find that is fair enough for compiling and for visualizing RTL. Yeah, so basically, this is a basic introduction of how you can use RTL, right? So how to compile it. So I think it is now my to be my step now back to my application. Back to the Quartus. I'm not sure. Maybe I will share my whole screen. All right. So basically, I would like to remind you that we are now using system Verilog, right? So we don't use wire, we use logic, and then we define it like that. So I would like to run, this is the problem that when I start, then it is not synthesized for some reason. It takes a little bit of time here, 4%. And then it says that the Quartus. Okay, maybe the problem is that the module name is not the same. So here is calculate, and oh yeah, maybe the I defined the file to be calculator, and here's calculate, so that's why. Let me see, calculator. Let's see. It would be very funny because I captured that the name of the file has to be the same as the name of the module, and this is how sensitive hardware programming is. Also not. Consists as a current design top partition doesn't contain any logic. So I think it got the first part wasn't successful. So we need to have a logic, of course. So I thought that initialize begin is a logic, but exactly not. So basically, I like the so let's have a one bit and let's call it signal A. Let's call it logic signal. So of course logic, and then you would like to write input, say inputs logic, and then logic input signal 2, and then logic input output signal 3, right? So and then after that the logic itself, can I use assignment or assign signal 3 equals to signal 1 and signal 2. Does it really work like that? So again, the module has to be the same name as the calculator. Top level entity name is calculator. Says the HDL syntax error. Oh, I think module does not have semicolon. Let me see here. So module, I this is my reference here, module, and then the name, and here is the logic 1, logic 2. Maybe there is something else. So initialize, okay, after initialize begin, and then end inside initialize begin, we can add whatever value we wanted to have, right? Okay. It's also not bad. We can, so after module name, we have to have a semicolon, but we have to have, after we write our logics or signal, then we have to have the initialize begin, and then I think I can have here a scan to jump analyze current file, save it. sure if there's autosave or something. Berg HDL syntax error at calculator 2. So line 2. Expecting an identifier input is a reserved key. Check for, yeah. So it's only appear immediately before. Let's see here. So logic without input. Yeah. All right. Okay. So we have signal 1. Can I have it like that? Oh no, wait. I think I would stop it. Just take a little time, and then just run this one here. Oh wow, now ours good. Okay, let's see here. To register is not supported. So those are registered, which is not supported. So maybe instead of that, me just write signal signal 1 equals 3 equals to 0. Can we have it like that? And we don't have 0, yeah. We have it like 1 bit because you have to okay, so you have to be a little bit concerned with what you are offering. So this is signal 1, and this is 1 bit 0, right? Or this at least at the 8 hexa AA, 8 hexa BB. All right. So what is index? Or link options. Okay, so maybe what I can go is to have it as 8 bits. From 7 down to 0. And then there are 8 bits binary. 8 bits hexa. And let's say they are A. Okay. Let's see. Let's see. So if you say that the signal is actually an array from four of 4 positions, and then maybe we can assign position of 0 to be that, right? It's okay. Actually, if we have a longer array is from 0 down to 3, up to 3, and then we can display, yeah. You know what? I think I can have a system very log online. Here we go. Here we go. Here we go. I think I have a module. Let's call it calculator. We have a initial start. I'll begin. And then we can write signal signal 1, let's say of 0 equals to, I don't know, 8 bits of AA, for example. And the same for signal 2 equals to 8 bits of AA, 8 bits of I don't know, 12. Oh, hexa, of course. This is a hexa. And this is a hexa. It's hexa. Oh, hexa 12. And then 8 bit of hexa 13, for example, right? And then end. And then, of course, at the end is end module. And then I think we need to run it. Need to save it. This is system Verilog. Can we run it? Please select valid tool as emitting. Okay, enable TL Verilog. Or this, right? I don't know. And then run. UVM 1.0, right? Was alles scheiße hier. Ganz ehrlich. Libraries, no libraries. Okay, yeah, so here. Open. Right. And then we have the Costa, Siemens, Synopsys, PC. You must log on. Oh, this is very shit here. Okay, do we just leave this? Maybe I will just copy what I have here and just compare it with what is here. So we have here the logic, and then we can initialize, then we can display with whatever we wanted to have, or we can have the logic and then we can initialize it, and then we can or we can initialize it like that. For so actually data replicate assignment, we can replicate it like that, or default also only specified indicator. Yeah. All right. So I want to make sure that I got it correctly. So this is the first way to signing it. The second way would be the signal of 1 equals to v values 8 x 1 to 8 x 1 through 8 x 8 of 8 bits of hex 15, for example. Or we can have a signal 1 equals to also the definition of 4 of 4 times of, I don't know, like 8 bits of hex 1 1 example. This is also okay. All right, so those are all okay. Let me see. So the best way is to open ChatGPT. Please correct. Too many errors. Use signal. Schätze. And there's no correct syntax for any array replication. It is four of, all right, without the inside it. Also, your array has four element. Only previous three values. Correct version will be like that. All right, okay. Sounds good. Sounds good. So those are the different ways of assigning the uh, yeah, the last one, which I really wanted to practice, would be signal one equals to um, so the definition of at position 0, we need to have E8 bits AA, and then at division 2 is 8 bits AB, for example, and so on. Yeah, and then default 8 bits AC, for example. Yeah. So this is also okay. This is also okay. So basically, I got something actually. I got that they are using here this playground, and that's actually that's not cool. That's not really cool. Um, Let me just write here and then run it. Oh, I have to log in. Let me log in. Hmm. This is the shit, yeah. So anyway, yeah, it's a tool, online tool. Yeah. So all right. All right. So thank you so much for watching, and see you next video.